Hey, Chemsters, this is not Leah for Leah.com. This is actually Mrs. Vanderwally for, I don't know, Mrs. Vanderwally. So anyway, we're going to start chapter 4 today, and we're going to talk about aromatic compounds. Aromatic, see, chemistry makes sense. Haha, little chemistry humor there. See the S-C-E-N-T-S, like odor, aromatic. Get it? All right. So that may be a clue right there. So why are these types of compounds called aromatic? Well, hopefully you figured out they kind of smell. Some good, some not so good. And so this actually brought about a very interesting thing. What makes these compounds the way they are? So it says, intro, what started off as a spice trade gave rise to an important branch in chemistry. Because in the Middle Ages, think of Marco Polo. What did? He went to China to bring back some spices. The trade in spices was very profitable. Otherwise, Marco Polo probably wouldn't have gone there if he wasn't going to make some money out of it. Spices and herbs are among the first natural products studied by organic chemists. If one could extract the plants of pure compounds with these desirable fragrances and flavors and determine their structures, one can synthesize them in large quantities, low cost, and without risk. So you don't have to travel to China anymore if you can make it yourself. So this was actually a well-studied, how can we do this so we don't have to go all the way across the world to get the fragrances and the spices that we want. So in 1825, obviously we're out of the Middle Ages in 1825, but they were studying this, and Michael Faraday, you might recognize his name. He's a very important scientist in both physics and in chemistry, electrochemistry. You'd see his name come up again. But anyway, he was also working in organic. He first isolated benzene with a formula C6H6, that's important, from coal gas in 1825. And he learned a few things from doing this. He found that benzene is very stable. And this caused a lot of people to kind of scratch their heads as, why is it so stable? So let's look at some facts about benzene. All right, well, first of all, what do we know about benzene? Well, again, the formula is C6H6. So what kind of a compound could it be? Could it be an alkane? Could it be an alkene? Could it be an alkyne? And look at the ratio of carbons to hydrogens. Obviously, with a C6H6, it could not be an alkane no matter what. How about CnH2n? It can't be really an alkene, not with one double bond anyway. How about an alkyne with one triple bond? Could it be that either? No. But what might we figure out is that it could be multiple bonds. So could we have an alkene with multiple bonds, 2, 3, 4 double bonds, or alkynes with, multiple bonds? So what I'd like you to do is try to draw at least 5 isomers of benzene. Pause this, scratch your heads a little bit, maybe confer with your partner, I don't know if you're all listening to this at the same time, and try to come up with a good 5 isomers. Now, did I have a complete list? No, but see what you can do. Remember, you need 6 carbons and only 6 hydrogens. Pause this. Let's go. All right, well, this is my list. Nothing too fancy here. I came up with tetraenes. I almost blew that there. Tetraenes with 4 double bonds on the 6 carbons, and that would give us the C6H6. So the first one would be like 1, 2, 3, 4 hexatetraene. The next one would be like 1, 2, 3, 5 hexatetraene. And then it'd be like 1, 2, 4, 5 hexatetraene. So that would be your first one. The next one I have as triple bonds, so I have dienes here, like 1, 3 hexadiene and 1, 4 hexadiene. I could have 1, 5 hexadiene, and it would still work too. So these are my versions, all right? Maybe you came up with something similar. Please note your triple bonds can't be next to a triple bond because of the number of bonds. So what do you notice about all these structures? They all have double and triple bonds. And what do you remember about double and triple bonds? We just finished that chapter. They're pretty reactive, aren't they? Okay, so let's see what happens here. Because it has multiple bonds, it is unsaturated. But if you recall, alkanes reacted by substitution. I called it the swap, okay? And alkenes and alkynes react by addition. Okay, when the things just add on to the double bonds and triple bonds, Markovikov's rule there. Remember that? So what happened? Michael Faraday and all his buddies there, they were testing out this new thing, benzene. They knew the formula C6H6. They figured out they had to have multiple bonds. And they go, okay, let's react this. Let's try to find something that we can put on here. Let's use bromine. What the heck? All right. So what do you think happened here? Benzene reacted by substitution and not addition. That's crazy, all right? Because remember, substitution is an alkane reaction. Addition is an alkene-alkyne reaction, but benzene worked opposite. Oh, now they're really kind of confused. What is going on here? So let's check out here. This is what they did. So they took some bromine, Br2. Remember we had like a little demo of that in class. And the bromine broke a bond, and one bromine joined on, and the other bromine took hydrogen away. Okay, do you remember that? So then the second bromination, all right, again, we get two bromines hooked on and two HBRs. This is like a double swap. Okay, so far, a little confusing. This is like an alkane, so what's going on? But it says here, like I said, what's going on? Benzene in the middle of the 19th century, so 1800s, was very much a molecule mystery. Michael Faraday, who was a very smart guy, couldn't figure it out. So why does a molecule with so much unsaturation, so many double, triple bonds, does not act like the alkenes? Why are there, whoa, 3 isomers of dibromobenzene and 2 that predominate, meaning I get 2 out of the 3 most of the time, and the third one's fairly rare? All right, what is going on? Answer, here we go. It's because of its structure. It took decades to figure out. So a guy named Kekulé, who was an interesting character, was the one that finally figured this out. So let's go to the next page and see what he did. All right, so the Kekulé structure of benzene. Frederick Auguste Kekulé. If you read about him, you kind of like scratch your head and wonder about him too. Twice it has been noted that he had breakthroughs in organic chemistry after dreaming about it. So he was trying to consider a structure for benzene. And apparently, don't ask me why, he was sleeping on the top deck of a double-decker bus, all right, in Germany. And don't know why he fell asleep up there, but apparently he did. And what was he dreaming of? He dreamt that a snake, in a sense, bit off its tail. So here, I'll see if I can do this. Here, oh, that didn't work. Okay, let's try this. So here is my snake, lovely snake, all right? So here is its head. See the head here? All right. And here, let's open up the jaws here, and it bites its tail. Okay, so you have this circular structure. So he dreamt about this, and he woke up and said, like, Eureka, I figured it out. I know what benzene must look like. So it's a cyclic structure. I bet no one there came up earlier on an isomer and making it cyclic, all right? So, but that's what he did. And let's look at a couple things here. So single and double bonds are alternating around the ring. What does that mean? Oh, there's a term from the past. It's conjugated. That means double, single, double, single, double, single. And this structure is highly stable. Therefore, it is highly unreactive. It doesn't want to, here, I'll move up here. There we go. It doesn't want to react very much, all right? It isn't, you know, it's pretty stable how it is. It wants to stay put. Okay, so Kekulé, I guess I left off his accent. Actually, a quick thing about there, Kekulé is actually from Darmstadt, Germany, which is on the French-German border, on the very western part of Germany. And Darmstadt Darmstadt was a very famous scientific, if you will, capital of Germany. A lot of scientists came from there, and there's even an element, Darmstadtium, named after the city, where a lot of cool chemistry came from. And so after he became very famous in chemistry, the German head people actually gave him like a royal title. He wasn't like an English king or anything like that, obviously, but they gave him a nobility class, if you will. And so from there, if you look at the Kekulé with the accent, that's a French name. So his family was probably French originally, but had settled in this western edge of Germany, or eastern, very eastern part of France. And so after the Germans gave him this title, he dropped the accent, would say Kekulé, and he adopted the name Kekule, which would be more German. So early in his career, they called him Kekulé. Later in his career, they called him Kekule. A little bit interesting there. So anyway, he proposed that the single and double bonds exchange positions around the ring. So rapidly, the typical reactions of alkenes don't take place. It's like, oh, for a second there was a double bond. Oh, now it's a single bond. Oh, now it's a double bond. And it keeps flipping, so it's not a true double bond. That would be extremely reactive, like we saw in the last chapter. So let's go back and look at the problem of this bromination that we talked about on the first page. So again, it is a substitution. It is a swap, okay? So what happens here? So the very first one, all right, here is my Kekulé structure. And with all the C6H6, and I put HBr. Sorry, I should have actually probably put in Br2. Can you fix this and make that here? Let's do it right now. Boop, 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 boop. Br. I hate doing this now. Oh, come back here. No, sorry guys. You can tell how much I love my board even when I'm not at school. Okay, here we go. Br. Oopsie, I've lost it now. Br. There we go. And we do have over here going to be an HBr. That's where I got the HBr from. So anyway, here, let me fix this up. Okay, so I just created the first structure. So I made C6H5Br plus HBr. So it again is the swap. So, excuse me, remember what we said, that we now can do it a second time, and how many different structures do we get? We get 3. So let's kind of see what happens here. So now we have this product that we got over here, brought it down here, and plus Br2, and look what I get. Do those structures look familiar? I had you watch Leia nomenclature, and you should recognize that there is certain terminology for the positions of those bromines. Do you recognize this as ortho? Do you recognize this as para? Oh, sorry, ortho meta. I'm sorry, this is meta. And then across is para. So those are our 3 possible structures if I were, to brominate this first bromination product, if you will, and do it a second time, and I get those 3 positions. Okay, so that's how that model can explain the existence of 1 monobromination, or 1 monobromine benzene, bromobenzene, and 3 dibromobenzenes. So there you go. So a little bit of this mystery has now been solved. So let's go back and look at this Kekulé structure. Notice a couple things. I kind of glanced over it at the beginning, but I want to go back and look at it now. A couple things. What do you notice about where the bonds are? So if I were to actually number these things, all right, so this is hydrogen number 1, hydrogen number 2, and let's do the same thing. This is hydrogen number 1, this is hydrogen number 2. Where is the double bond? Well, for 1 second, it's between 1 and 2. And for the next second, it's not. So if you notice that the bonds that are alternating are not in the same position over here. And notice this double arrow right here. This is what is called a double arrow for the idea of resonance. Oh, we've talked about resonance. Remember that opera singer? Remember that bridge? That's resonance. So what's happening? Those double bonds are flipping back and forth and back and forth and back and forth and back and forth, creating such a stable structure. So let's kind of go down here. So the resonance model for benzene. All right, calculate these two structures for benzene differ only by the arrangement of the electrons, those pi bonds. Again, this is a definition of resonance. Instead of writing the equilibrium arrow as above, like for a reaction, okay, like here, we use the single bond, but write the double-headed arrow to indicate a resonance hybrid, okay? So let's see what the next page brings us. So, because of resonance, all benzene molecules are identical. So what about this flipping back and forth? Well, benzene is more stable than the calculae. There are no true double or single bonds, but instead each bond acts like a 1.5 bond, someplace between a double and a single bond. Okay. Benzene does not react chemically like alkenes because each bond is identical. Like alkanes. Alkanes, each bond is identical, and alkenes are not. You have some double, you have some single. Okay, so that explains that kind of mystery too. So let's talk about some physical properties of benzene. Benzene is planar. If you look at it, do you remember your, when we kind of made some things here? I guess you just saw my other property here. This is a planar thing. So all the carbons are in the same plane and all the H's are in the same plane. Look at what's going on here. That we have sp2 bond here. We have a 1s and sp2 bond here. So this bond between the carbons is a 120, just like in a hexagon. And then the hydrogen comes off at a 109 angle. Do you recognize the 109? And the angstrom, the bond length, is also kind of short. And I'd say this is a 120 also, I believe. So the angstrom is a 1.09 angstrom, so it's a short bond there. So all carbons are sp2 hybridized. All carbon-carbon lengths are identical at 1.39, and the carbon-hydrogen are 1.09 angstroms. That's just a unit of measurement, 1 × 10⁻10th meters. And it is colorless. Boiling point is 80, melting point is 5.5, and the other physical property you should know about benzene, it stinks, all right? That's kind of why they call it aromatics. So now we go into the orbital model of benzene. We're looking at the pi and the sigma bonds here. So notice that each one is sp2 hybridized, and that's what your pink is your p bonds. And so that forms like the circle on the top and on the bottom. So you have this ring on the top and on the ring on the bottom. That's your pi bonds right there, okay? So it's like you have a sea of electrons on the top where they're all being shared equally. It's not a single bond, double bond, single bond. It's all that 1.5 bonds going around here again, causing it to be extremely stable. So it says here the sigma bonds are formed by the end-on overlap of sp2, and your pi bonds are overlapping the 6 2p orbitals for continuous pi cloud. And that's really what they call it, is a pi cloud. Again, giving it its stability, but giving it those extra electrons for those substitution reactions to occur. So let's go ahead and turn the page and see how we can now more accurately symbolize benzene. Okay, so there are two symbols used to represent benzene. One is the calculae structure, or the Calcul if you want to talk German, and the other one is this hexagon with a circle in its center. This is representing that delocalized pi electrons, or that pi cloud. So here again we show the double bond, single bond conjugated part, and notice the double arrow. This is your resonance. And over here we just say, all right, this is an easier way. This circle here is showing you that pi cloud of electrons. And probably this is a more truer representation of benzene, but these structures help a lot when we do reactions. Now notice with this, we did not put any hydrogens on here. Please know they're there, all right? But again, it's a lot easier. It's kind of like doing the line notation. We know they're there, but let's just kind of leave them out. And again, the circle emphasizes the fact that the electrons are distributed evenly. I think I've already said that. So the calculate symbol reminds us that there are 6 pi electrons in benzene, and if the calculate symbol is used, then remember that all double bonds are not in the fixed position, and they're not even true double bonds at all. Again, that's why they do substitution and not addition reactions. So what exactly is an aromatic compound besides the fact they smell bad? All right, so the criteria for aromaticity were recognized in the early 1930s by Erich Hückel, another good German scientist there. And so to be aromatic, you must have a couple things here. So to have one occupied 2p orbital in each end of the ring, to be planar or nearly planar, so the overlap with all the 2p orbitals in the ring is continuous or nearly continuous, and it has 2, 6, 10, 14, 18, and so forth, so add 4 each time, pi electrons, and have 2, 6, all right, so you add 4 each time. And why did I circle 6? Because that's benzene right there. All right, so that's probably the most common one, but not the only one. Fourth in this cyclic arrangement. So that's another key idea right here is this word cyclic. So it needs to be in a cycle, all right, or in the ring structure. Okay, so benzene does meet this criteria. If it is cyclic, planar, has 1 2p orbital for each end of the ring, has 6 pi electrons, all right, the aromatic sextet, in the cyclic arrangement. Aromatic compounds are exceedingly stable because the pi electrons are spread out. So now, after all this, 20 minutes later, we have discovered the mystery of benzene. We've now figured it out. And so the other polycyclic aromatic hydrocarbons are aromatic, meaning they smell, as well. Okay, so let's see what the next page is. Okay, so problem number 1. Determine whether the following fit the criteria of being aromatic or not. All right, so take a minute out. You may want to pause this when I'm done talking here and flip back to the prior page and see which one of these structures meet the criterion. Okay, so pause this. Let's see how you do. All right, so benzene, I sure hope you know, is aromatic. We've been talking about it for the last 21 minutes now. So, yeah, benzene is aromatic. What about hexatriene? Is it aromatic? What did you say? Did you say no? You're right, because it's cyclic. Or I'm sorry, it's not cyclic. It's not in this ring. So hexatriene is not. It has 6 pi electrons. That's true. It has, you know, the conjugation alternating double single that works, but it's not cyclic, so it's not an aromatic. What about the cycloheptatriene? What do you think about that one? The answer is no. Why not? Because it's not conjugated. Do you see this area right here? It's not like double single, so that doesn't work either. What about naphthalene? All right, does it fit the criteria? Is every other bond alternating double single? Yes. Is it cyclic? Yes. Does it have the correct number? Go back on the prior page. All right, remember it had what? 2, 6, 10, 14. How many pi electrons does it have? It has 10, so that works too. Naphthalene is aromatic. And by the way, here's another thing to prove it. Naphthalene is otherwise known as mothballs. What do you know about mothballs? Oh, they smell pretty bad, okay? So they have definitely a fragrance. So how about tetraene, all right? There we go. It looks really kind of weird, doesn't it? Does that fit the criteria? It's alternating. It's cyclic. But what's wrong with that? It has 8 electrons, not your 6, 10, 14. All right, so it's not aromatic because it has the 8 pi bonds, and aromatics don't have 8 pi bonds. Okay, so you can kind of see how you did there. So which ones are aromatic? I think I put AKA mothballs. Okay, so I put the answers underneath instead of along here, so I left that part blank. Sorry, guys. So now let's see what's going to happen here. All right, so nomenclature of aromatic compounds. I tell you what, why don't we stop here today? And I sure hope I'm back next time to start. But as maybe a preview of things to come, do you remember what we said about Leia? Do you recognize these again? All right, maybe you can spend the rest of the bell, because I know I didn't use up your whole bell, and go on what's it called, Quizlet, and I put all these structures on Quizlet. So I put a link on your Schoology, and start memorizing these. Okay, so these are those same ones that Leia told you about in her videos. So start committing these to memory. Yes, you have to know them. So that concludes my Not Leia presentation. I hope this was helpful, and how about my closing response is, I'll steal it from Montel Brown, don't wait to be great. Take care.